There are a few good questions during the break. Let me just clarify some of them. First one is this one here. How do I know that CM0 is less than 0 for a positive camber? Well, there are two ways of looking at this. One way is you can put this into a wind tunnel, and if it's a positively cambered airfoil, most probably you will get CM0 less than 0, okay, for this airfoil. Or you can do a computational analysis. Let's say you can do a panel method, like we do in aerodynamics, right? You put forces, you put panels over here. You can put vortices or sources and things and sinks and things like that in order to analyze this airfoil. And again, you will find you can calculate lift, drag, and moments. Now the second question is, of course, with respect to what point do we find these moments? Because you can take a moment, you know, at the end, an airfoil has forces and has little pressure points everywhere, right? And you add them up together and you obtain a lift and a drag, right? You obtain a lift and a drag. And then with respect to which point do we calculate lift and drag on an airfoil? Where do you add these forces and moments? Wherever you move those lifts and drags, you also obtain a moment, right? Isn't it? Okay, so which point are we using for airfoils to calculate? Let's say I have an airfoil like that. And I tell you this is the lift and this is the drag. What point am I using to do that? I mean, this doesn't really exist, does it? I mean, it's more like this. This is your airfoil, and you have these little pressure points. And you add them all up together. If you add them together, you really obtain something like that. You add them together and you say, oh, okay, so now I have this and I have this. In fact, if you add these two together, it's in reality, it's just one force, right? This is just one aerodynamic force that we have. Okay? If you add these things together, lift plus drag, you will give you this, isn't it? Okay, but if you add these things together, if you add them together over here, you move those forces to this point, they all come with a moment, and you will create a moment, isn't it? Same thing over here. You will just keep moving them. It will come with a moment, and that will be a moment. So what point are we using in aerodynamics to define lift and drag? At what point do they act, do we say? When I say lift is, if it's such and such for this airfoil, what point am I talking about? Aerodynamic center. So what is the definition of the aerodynamic center? What moment is zero? The moment is zero at aerodynamic center. Don't say that in the third grade. That's not correct. What is it? What is the definition of the aerodynamic center?
The point where the moment is not changing with the changing angle of attack.
Ah, so that's good. The change with respect to angle of attack is equal to 0. That's the aerodynamic center. Right? Okay, but we keep saying that Cm alpha must be negative. So how is that? Then this is not the aerodynamic center that I'm talking about here. It cannot be the aerodynamic center because Cm alpha is equal to 0 with respect to the aerodynamic center. But this moment here, with respect to what point is that moment? How can it be? What is the definition of the M moment that we have been talking in this class? It is the moment at the CG. It is the moment at the CG that we are talking in this class. So Cm alpha is equal to 0 is if you take the moments at the aerodynamic center and put your coordinate system at the aerodynamic center. But in our class, what we are doing so far, the moment is with respect to the body fixed coordinate system, and the body fixed coordinate system is attached at the CG. And therefore, whenever I say Cm alpha, I'm talking about the CG still. Because Cm alpha would be equal to 0 if that point would have been the aerodynamic center. Does that make sense? Okay? We will talk about this more in the next hours. There was one more point. Do you have any questions on that, first of all? I know it suddenly got a little bit confusing because I immediately went into this airfoils. We will talk about the airfoil in a second now in great detail. But I had to go through this airfoil to explain you why we have a horizontal tail on airplanes. Okay? So that's that. A second thing is, I keep telling on this picture, I said, let's say alpha is equal to 0, v infinity, I need a force moment. And this is not a trimmed flight condition. Okay, this is not a trimmed flight condition. Alpha equals 0 might not be a trimmed flight condition. Okay, so let me see if I... You know, when I gave you this example here at the beginning of this class, I said, let's say I have an airplane where v infinity is, it's in a trimmed, oh no, okay, not this one, I'm sorry. Yeah, it was probably this one. So when I tell you that, basically when I tell you that for an airplane at alpha equals 0 at v infinity, for the whole airplane, I must have a positive Cm0. This does or is not necessarily a trimmed flight condition because alpha is equal to 0. This is not a trimmed flight condition. In trim, Cm must be equal to 0, right? So for this airplane, a trimmed flight condition would be something like this. I would have v infinity, I would have alpha, some alpha trim, so which is not 0, okay, which is not equal to 0, right? And in this case, yes, Cm must be equal to 0 because now this is a trim. But this might not necessarily be in trim. It is just a condition where I take the airplane, force it to alpha equals 0, blow air, and then look at the moment. I'm just saying if in this flight condition, Cm0 must be positive. Why does it need to be positive? In order to justify this, alpha versus Cm. So this is alpha trim, and Cm alpha is less than 0, and Cm0 is positive. In order to justify this, at alpha equals 0, Cm must be equal to 0. The question is, why not have 0 moment at alpha equals 0? Well, if you have 0 moment, then it means at alpha equals 0, Cm is equal to 0, you are here. So, and that doesn't make really sense because you will have Cm and you have alpha, and suddenly you are saying at alpha equals 0, Cm must be equal to 0, then you are here, okay, then which means you are trimming at alpha equals 0, right? I mean, it could happen so, but we really don't like that either. We want to trim at a positive alpha, and therefore you need this. So this is not necessarily a trim condition. That's what I'm trying to say here. You understand that story. This is very important. That's why I'm going slow here, and you need to understand this very well. And the moment that I'm still talking about here is still the CG of the aircraft. Okay? The CG of the aircraft. The moment Cm is still the non-dimensional moment. Non-dimensionalized around, non-dimensional trim moment. Not trim moment. It's ridiculous. It's still the non-dimensional moment. Non-dimensionalized M. And that is still the aircraft at the CG with the body y direction, x body, and z body. And M is still this moment. And this is L, and this is N. Okay? It's still this one. It's still this one. Cm alpha is still there. It's still around the CG. Okay? So when someone says the aerodynamic center is the point where the moment is not changing with respect to alpha, which means Cm is alpha is equal to 0, that moment is not this moment. This moment is the one at the CG, not at the aerodynamic center. Understood? Okay. Any questions? Okay, as I said, this is something you really, really have to understand, these parts. So, laptop would be this one. Hopefully this is going to work. Work. Okay, there you go. So this is the aircraft of the Wright brothers, you see? Wings, the propeller pushing you forward, and where is your horizontal stabilizer? Here, you see? You need to have a horizontal stabilizer. The moment arm is quite small, you have this big wings, but still, you needed that thing. And where's your vertical stabilizer? It's at the back. Right? So how did this evolve? We evolved the airplane where the wings are in the front and you have a big fuselage and the horizontal tail and the vertical tail go all the way to the back. And because they have now large moment arm, the area of these surfaces can be smaller now. They don't have to be as big as this one because the moment arm is small here. Although this was still a statically unstable airplane, but yet it was possible to fly. Okay? Look at this one, 1902. It's the glider. Glider, there's no engine, right? Still you have something that gives you stability in the horizontal direction, static stability, or at least helps your stability. Look at this one, you see? It's in the front. The horizontal stabilizer, and you have the vertical stabilizer at the back, 2 wings, and you're gliding down a hill. And it is controllable, we call it controllable. Although it might be unstable, you can still control the aircraft. You see? Here's another nice picture. You see the moment arms, right? Here's the moment arm, here's the moment arm, vertical tail, horizontal tail. As I said, what we do now, we take the horizontal tail and the vertical tail, send it all the way to the back, and therefore we can make them smaller, right? And we have a large moment arm. And this is what it looks like, 1903, with the engine. You see? Any questions? Okay, so let's go back to our thing here. Okay, now we are going to look at this from on the whole airplane. Now we need to look at the airplane. So synthesis of pitching moment and lift. So this is now our new topic, and we are going to look at this whole business a little bit more careful, a little bit more one by one. The way we're going to do this is we first are going to look at the wing itself. I mean, I tried to explain it to you with airfoil, but we'll look at the wing. After that, we're going to look at something called the wing body. So it will be basically a fuselage that is attached to a wing, so we call it a wing body. And then finally, we are going to look at the wing body plus the horizontal tail. Okay, so this is now our plan for the next 2 weeks, I guess. We are going to look at the wing alone. Then we are going to progress into the wing body, which is pretty much the same thing, except the aerodynamic shape is a little different. And then we are going to progress into wing body and horizontal tail. And that will give you the whole airplane, hopefully. So this will finally be the whole airplane, and we look at the stability characteristics of the whole airplane. Okay? So let's start with the first one. Let's start with the wing. Okay, let's look at a pure wing. Okay? That's the idea now. We're going to look at a pure wing. So this is what we are going to do. We are going to, let me draw a big wing here, a big airfoil. It's not a pretty one, but it's okay. So let's put the aerodynamic center here of this airfoil. Let's say this is the aerodynamic center. Okay, and the aerodynamic center is, as you defined, the point where lift and drag is acting, and there's a moment associated with it, but the moment does not change with alpha at the aerodynamic center. This is how we define in aerodynamics this point. Let's call this point the CG. I know it's kind of off in the picture, it's kind of in a weird place, but it's fine. It doesn't really matter at this point. And this is kind of the chord line. All right. And let's say we will have a V infinity like that. And let's call this angle alpha wing. Alpha wing. Okay. And now I'm going to look at the distances right here. Let's do this. Let's do a longitudinal distance here, and let's look at that, and let's look at that. Okay, so this whole thing here is, of course, the chord. That's the chord. Okay. And let's define this one here. That's the height of the CG with respect to the chord line, so that's one we call Z. Okay, that's the distance. This one here HC bar, so it's a fraction of C bar, okay? So it's, for example, 40% or 60%. So 0.6 times C bar will be that distance. 0.2 times C bar will be that distance. H is just the percentage there. And this part here, again, we call it in terms of a fraction, HN C bar, okay? So H and HN are the fractions with respect to C bar. So this might be 0.6, this might be 0.2, whatever those numbers are, but we take it as fractions of the C, of the chord. All right? So if this is V infinity, which way would be lift and drag? Lift would be perpendicular to V infinity, so this would be lift, right? And this would be drag. That would be parallel to V infinity, so that would be lift and drag, okay? And as you said, at the aerodynamic center, there's also a moment, and this would be a positive direction of the moment, and let's call it the moment at the aerodynamic center of the wing. Okay, so MACW is the pitching moment at the aerodynamic center of the wing. Pitching moment at the aerodynamic center of the wing, and therefore by definition it is constant. And therefore it is constant with alpha, right? That's the definition of the aerodynamic center. It's constant with alpha, but it's not the moment with respect to the CG. It's the moment with respect to the aerodynamic center. So we are interested in the moment with respect to the CG. Understand? So I'm going to take the moment with respect to the CG. So when I say M, this M is now the moment at the aerodynamic center. When I say CM, that big M, that is at the CG. It is still the body fixed coordinate system and so on and so forth. Is that okay? All right, so any questions about this picture? So this is my pure wing. So what we like to do now is we are going to take total moment about the CG. Take total moment about the CG. And that one I will call M wing. Okay, this is not now a partial derivative. This is the total moment about the CG of the wing. Okay. So let's take the moment MW. So I'm just going to take the moment with respect to the CG. Okay. And just add everything, right? You have these two forces and add everything, and you have the moment. So the moment, it will come as it is because that's constant, right? It just moves over here to the CG. Plus, now it will be the lift. Let's call this lift wing and drag wing so that we don't get confused, okay? This is the drag and the lift of the wing. So lift wing and drag wing. So lift wing cosine alpha wing plus drag wing plus sine alpha wing h minus hn times c bar plus L wing sine alpha wing minus d cosine alpha wing times z. Okay? Quite straightforward. So this is the total moment around the CG. That's fine. But since we are going through an exercise here in class so that we have some meaningful, we are trying to get to some conclusions, I will just make some really fast and easy assumptions here. One of the assumptions is that that Z is small. Okay, I'll say Z is small. So Z small is basically this one. The CG and the aerodynamic center, in most airplanes, they are kind of aligned. Okay, there's not much. The CG and the aerodynamic center, they are somewhat aligned. But even if they are not aligned, we can assume them to be small. And if it's not small, you cannot make that assumption. Every time I make an assumption, it feels like I'm cheating. I'm just saying that the CG and the aerodynamic center are mostly aligned, or it's very small. If it's not aligned, what then? Well, then you cannot not make that assumption. Then you need to keep it in your equations, okay? It's as simple as that. So we're going to say this is small. We're going to say this one is small because of the because it's a sine alpha, and alpha is not very big for airplanes. I mean, you see, I made here almost 30 degrees, but we all know that at 30 degrees an airfoil will probably not survive. It will stall long before that, right? So most of the time the alpha is about what, 5, 6, 7 degrees. So therefore sine alpha is quite small. So if you make those assumptions, things become a little bit more simplified, and this MW could be the aerodynamic center of the wing plus lift of the wing times cosine alpha wing times h minus hn times c bar. Okay, so this is still the moment of the wing around the CG. So non-dimensionalize this, non-dimensionalize with 1 over 2 rho SC bar V infinity square. So it's a steady condition, so it's the V infinity. If you non-dimensionalize, what you will get is Cm, okay, of the wing, let me write wing, is equal to Cm at the aerodynamic center plus Cl of the wing, and this is now the lift coefficient, Cl, h minus hn of the wing. Okay. Let me go one step further. Cm wing is equal to Cm at the aerodynamic center, and that doesn't change, right? The moment at the aerodynamic center doesn't change, plus alpha wing times Cl alpha of the wing, h minus hn of the wing. Excuse me? Well, alpha is small, and therefore this is close to 1. Okay? No, you can keep it in the equation if you want. You can have a cosine alpha here. It's just that things will get a little bit more complicated. But since alpha is small, let's say 5 degrees, believe me, it will be 0.98. So it's not a bad assumption if you just say 1. Okay? If your airplane flies at alpha equals, I don't know, 4 degrees, 3 degrees, what is it? Alpha 3 degrees is nothing, right? It's really 1. So let's keep this on the side. This is the moment. Okay, let's keep this on the side. This is the moment of the wing. Moment about CG of the wing only. Okay. Any questions so far? Now, if I would have not an airfoil, but some sort of another aerodynamic shape, would that calculation be any different? For instance, if this wasn't a wing, but if this was, I don't know, something strange, I mean, instead of this, this calculation was done for this, right? But let's say instead of this, we have something that looks something like that. Sorry, looks something like that. would that calculation be any different? We would still have an aerodynamic center, we would still have a CG, we would still have V infinity, we would still have alpha. The calculation would be the same, right? We would still arrive at the same equation. So what I'm proposing is, instead of looking at the wing only, let's look at the wing body. This is the wing, and there's another airfoil over here. So it is a three-dimensional thing, but I'm looking at it from the side, and we would obtain something very similar to this, an equation. So what I'm proposing basically is that for a wing body, we could really write this. Wing body is equal to Cm at the aerodynamic center of the wing body, plus alpha of the wing body, plus the lift curve slope, h minus hn of the wing body, where this one here is now the lift curve slope. Okay, it's the lift curve slope. So what I'm just saying that, a wing is an aerodynamic shape, but if you add a body, the equations will not change. It's just another aerodynamic shape, and therefore I'm going to use the same equation for that. What's going to make a major difference now is the tail rotor, okay? Not the tail rotor, the horizontal tail. If I add the horizontal tail, that's going to make a major difference now to the equations. So this would be the same thing for the wing body. So what's going to make a major difference now is if I add the tail now. Wing, body, and horizontal tail. Okay? So that is going to make a major difference. So now we can do this. This is my wing, or my wing body, whatever. Okay. Still, this would be the CG. Okay. And let's put a horizontal tail exactly here. Let's call this distance LT. And that is the distance to the aerodynamic center of the horizontal tail. Okay? And let's say V infinity is like that. So that distance, that angle would be alpha tail, not this one. Okay, that would be alpha tail, the angle of attack of the tail. As a result, you would have a drag of the tail, and you would have a lift of the tail. Okay. And that distance is still ZT. Okay. All right, so let's look at, we can look at a number of things. The lift that's generated at the tail, we can write it the way we always write it, rho v square the tail surface times CL of the tail. The drag of the tail will be 1/2 rho v square st times cdt. The lift of the wing body, though, will be 1/2 rho v square s of the wing body times CL of the wing body. Right? So the total lift on the aircraft is lift of wing body plus lift of the tail. Right? And if you non-dimensionalize this, you arrive at that. CL is equal to CL wing body plus ST divided by S times CLT. If you non-dimensionalize this. Yes? Say again? What angle difference? Which angle are we talking about? Which angle?
Okay, so we are just taking it perpendicular to V infinity.
Yeah. Lift has to be perpendicular to V infinity. The direction might change, right? It might, alpha t, it might be all the way this way or that way. We don't know all this yet. We don't know about the directions. I'm just plotting. I'm not saying this is an airplane in trim. I'm not saying this is the best flight condition for an airplane. I'm just using my sign convention. If for stability, for example, this has to be a negative number, it will show up in the equations. The equations will say this has to be a negative number for stability or something. Okay? So I could have done it the opposite way. I could have done V infinity coming from the top and say, and put lift down or something. I mean, as long as you're consistent with the directions and with your sign convention, the equations will be fine. Okay? So, just one thing, when we non-dimensionalize lift, or CLT, we non-dimensionalize it with the tail rotor surface. Okay? So, and same thing for the drag. But if you do for the wing body, then you have to non-dimensionalize it with your reference area, which might be the wing. Okay? So this is the lift for the wing body, this is for the tail. So you add them together, that's the total lift of the airplane. All right? So what we are just adding them together. But now when you non-dimensionalize it, it will not be CL wing body CLT, right? Because one is non-dimensionalized with ST and the other one with S. So if you non-dimensionalize the total lift with S, then you will have an ST divided by S on this side. Okay, that's where this is coming from. So this is the total lift. But what we are really interested in the moment, not necessarily in the lift. right? We really need to see what's happening to the moment that comes from the tail rotor. So what we are going to do now is we are just going to calculate the moment of the tail about the CG of the aircraft. Moment of the tail about the CG of the aircraft. And that will be now LT, but it will be a minus. Let me just write it down. LT cosine alpha t plus dt sine alpha t minus zt times dt cosine alpha t minus lt sine alpha t plus the moment aerodynamic center of the tail. Yeah, one thing I forgot over here is, of course, I have a fixed moment around the aerodynamic center, moment aerodynamic center of the tail. Okay, it's a constant moment that is at the aerodynamic center. So, can you see that this term is a negative one? I mean, look at this one real quick. If that's the CG of the airplane, and this is the moment, it will generate a moment like this, so that would be a negative moment, right? Because that's a positive moment. Y body is in this direction, so that would be a negative moment. So this gives you a negative moment. So that's why you have this negative thing over here. Okay, over here. It's negative LT times this, that's the big moment. ZT is that little distance over here. We could take this as 0 because ZT could be very small, and you're ending up with this equation. Okay? So you can make a lot of simplifications here, or you don't have to, but we are going to make them anyway. Since we are just here to do an exercise, we're just going to say this is small. Okay? We're going to say this one is small, this one is close to 1, okay? And since the tail is a really small, compared to the wing, it is rather small, this one is also small, and you are ending up with the simplest form you can ever imagine. It will be the moment of the tail about the tail rotor is minus LT times LT. Okay, that's it. So, and the lift of the tail is it's minus LT times CLT times 1 over 2 rho V square S tail. I mean, we made really big simplifications. I just wanted you to see the whole picture. But compared to the wing, this will be small, that will be small, that will be gone. So you basically have the moment arm times the lift that will give you the negative moment, right? It's really stupid, actually. We could have done it from the beginning, but I want you to see the whole equations. So, okay, so that's that. And instead of LT, we could be writing the non-dimensional, it's still the dimensional form, but in terms of CLT. CLT times 1 over 2 rho V square ST. This would be the moment of the tail. Do you have any questions so far? All right. We are about to come to a good conclusion with all this. So, next, non-dimensionalize the moment. Non-dimensionalize the moment. So, the moment MT. So, here's what's going to happen. CMT, the non-dimensional moment of the tail, is simply mt divided by non-dimensionalized by 1 over 2 rho v square sc bar. Okay? So you add this whole thing, you will get what? Minus LT CLT 1 over 2 rho v square st divided by 1 over 2 rho v square sc bar. Okay? That's gone, this is gone, these are all gone, gone, gone. And CMT is equal to minus LT divided by C bar times CT divided by S times CLT. And this is the non-dimensional moment caused by the tail at the CG of the aircraft. Okay? That's the moment. Understand it? It's a non-dimensional moment caused by the tail at the CG of the aircraft, and it's simple as this. LT is a distance, right, from the CG to the aerodynamic center of the horizontal tail. C bar is the mean chord of the wing. ST, area of the tail. S, reference area of the wing. CLT is the lift coefficient of the tail. Okay? Now, why did I write this in this form? There's a good reason for it. Because this number is an important number. Okay? We call it VH. And it is the horizontal tail volume ratio. And it's an important number in aircraft design. We use this number when we design airplanes, and most airplanes, most commercial airplanes, give and take, the horizontal tail volume ratio is approximately the same for a lot of airplanes. So if you want to start with an airplane design, one of the things you need to be careful is that the vertical horizontal tail volume ratio must be approximately constant. So what does it say? On the top, you have the moment arm. And here, you have how big your tail is. Okay? On the bottom, you have how big is my wing, like the chord, and how big is the surface area. So it is related to how big my wing and how big my airplane is compared to how big my moment arm is and how big the horizontal tail surface is. And when I tell you for most airplanes this number must approximately be similar at least, that means if you have a big airplane with a big wing and a big chord, you also need these two numbers to be comparably big. Okay? Now, which one of these must be big? Well, they must either this or that, because you're multiplying, right? So either you have a short moment arm and a big horizontal tail, okay? Or you have a long moment arm and a small horizontal tail. But the multiplication of these must be comparable to the multiplication of these ones. Okay? So if you have a big airplane, and these are big, this must also be big. If it's a small airplane, they can also be small. But which one is smaller, LT or ST? Well, that's up to you, designer. If you make a short airplane, the surface must be big. If you make a long airplane, the surface can be small. So therefore, when you start building an airplane or designing an airplane, you typically start with a tail volume ratio, okay? And then size your aircraft such that this number is met, okay? So the moment that comes from the tail is then therefore VH times CLT, okay? And the horizontal tail volume ratio is LT times ST divided by C bar times S. So if you look from the top, you might have an airplane with a wing like this. So if it's a short airplane, you also need a big horizontal tail. Or you might have a real slender airplane with the same wing. Then your horizontal tail can actually be a lot smaller because LT is now a lot larger. And this ST has to be large, and this ST can be a lot smaller, you see? So if you had an airplane that was really long like that, and you had the same wing, you could really have a small tail. But if you had the same airplane with a really big wing, well, this one must still be big. Okay? And all these four airplanes might have similar VH. Okay? And, you know, we have built so many airplanes. We kind of know what the VH should be for a passenger airplane, or what the VH should be for a fast-moving fighter airplane or a cargo airplane. We kind of know what the VH should be. So, you know, sometimes people ask, well, most airplanes, they look alike. They kind of look similar. It would be really funny to have a slender airplane like this and a really fat tail, right? And you would say, oh, this is a funny-looking airplane. The reason they are all so proportional is because the VH in the horizontal tail is, in all of them, approximately similar. Okay? So when you start designing next year in aircraft design, you will pick a horizontal tail volume ratio when you start your design. And then you will try to play with these distances and these tails, these reference areas, such that you will met that tail volume ratio. Okay? And you can see it in this equation. I mean, look at this one. The moment of the tail is VH times CLT. And CLT is simply, you know, the lift coefficient. And there's something to do with the airfoil angle of attack and so on and so forth. But in terms of design, VH is such a critical number. Any questions? Okay, so I want to finish this lecture now, and we will start looking at this a bit closer next week, because we didn't really look at stability yet. We're going to look at stability. Okay?